In today's video, we're going to take this point, move it in a straight line that goes in random directions, and have it be trapped within a spherical region by this sci-fi material that figures out the position where the sphere is going to go and blocks it, causing it to reflect back within that given radius. We're going to be using simulation nodes, and it's going to be a little math heavy, so I'm going to try and explain exactly why we're doing what we're doing, and this effect almost broke me trying to find out how to create it. So I'm really glad to be sharing it with you. And with that, let's actually begin the tutorial. In our default scene, we're going to bring our cursor to the junction of these two windows, click and drag to create a new window, and we'll change it to the geometry node editor. Then we'll press this plus button to create a new geometry node tree, zoom in, select the group input, and press X to delete the default cube. Now the first thing that we'll do is actually do the simulation for the point that moves around in random straight lines and is blocked by a spherical radius that's going to be imaginary for now. So let's do that by searching for a points node by pressing Shift A and searching for points and plugging that into the group output. Now we have a single point that is present. Next, we're going to simulate this point to move according to some given velocity. So I'll press Shift A and search for a simulation zone and then plug that in by plugging the geometry into the simulation input and taking the output and plugging that into the group output. Now we essentially need to update the position of this point with respect to some velocity, and we've done that in various previous tutorials. You should definitely check out other simulation nodes tutorials from the playlist linked right now to get a better grasp of why we're doing what we're doing. But let's go through how we're going to do this. The first thing is, for velocity we need the final position and the initial position, and we have to subtract them. So to find the initial position, we have to capture the attribute. So we search for a capture attribute node, plug that in, and change this from float to vector. Then we're going to search for the position node and plug that into the value, and this attribute is going to give us the initial position. Then for the final position, we can directly search for a position node, and whenever the right hand side gets plugged into the simulation output, that is going to be our final velocity, but we will get the final position from this particular node. So now we can find the velocity by using a vector math node and changing it to subtract, and then taking the final position, plugging it into the first socket, and taking this attribute, which is the initial position, and plugging it into the second socket, and plugging this into the simulation output. Now this vector, if we want to change the name, we're going to change this panel to node, and if this is not present, then you can press N to bring it up, and then just select the simulation output and go down to this vector and change the name to velocity, just so that we are clear with what this particular output is. You don't have to change the name, but it helps to maintain uniformity. Now we have the velocity, and we need to actually move this point according to the velocity that we calculated. So to move the point, we can use a set position node. So take this set position and plug it in after the capture attribute. Now for the offset, we can directly plug this velocity into the offset, and now if we press play, nothing's going to happen because we haven't given it some initial velocity. So we go ahead and give it some initial velocity, and now it's going to calculate the velocity according to this velocity, and it's going to loop back, and it's going to keep moving in the same direction. So we can give it an initial velocity of 0.2 and then start off figuring out whether it's actually hit the outer bounding sphere and get it to come back. So to do that, we actually have to define what the outer radius is and the radius of the sphere. Now since we're going to be using those two values multiple times later on, I'll just store them in two value nodes by searching for a value node and then zooming in, selecting it, going to the node panel here and labeling this as bounding sphere and giving it a value of maybe 5 meters. So this is going to be the radius of the outermost border, and then we'll select the node, press Shift D to duplicate it, and change this one to smaller or bouncing sphere, and this one we're going to change to the radius of the smaller sphere, which is maybe 0.5. Now to check if this ball has gone beyond the bounding sphere, all we need to do is find the position of this sphere and check if the position is greater than the radius. So that's fairly simple to do, but there are a few caveats that we have to take care of, which we'll do once we face the problem. So first, the normal way how we generally do that is by simply searching for a compare node and then comparing the current position, which is present over here, with the radius over here, and we can say if the actual position is greater than the radius. So let's actually plug this up here and the radius in the second socket, and we say if it's greater than, in that case it should not be using this set position, it should use a different set position which actually pushes it back and determines a new direction for it to be moving in. So for that, we have to actually switch between this set position and another set position. So let's actually duplicate this set position node and take this geometry from here and plug it in, and we'll play around with the offset later on. But first we have to figure out how we're going to switch between these two set positions, and we can do that by using a switch node. So let's search for a switch node and plug that in over here. So now if it is lesser than this value, it's going to use this set position, and if it's greater than the current radius, then it's going to use this second set position. However, the problem is this switch node takes in a circular socket, which means it cannot take in a field value which changes for different points. But since we're using the position and the capture attribute over here, this capture attribute is taking the position for every single point in the geometry. Now granted, we do have only one point, but it is still real geometry, and technically we could have multiple points. Blender does not know how many points we have, and that's why this greater than node is also giving a result as a field, which means it could be for a single point or multiple points as well. And if we actually try to plug this into the switch, you see it turns red, and even if we have a single point, it's still going to remain red because Blender does not know that it's going to remain only one single point. So because of that, we have to find out how we can make sure that this greater than node is going to have only a single value coming in here, which is going to be the position of this particular point itself, and that is what we can use as the value that goes into the switch input. So the way we're going to overcome that is by searching for a bounding box node, and this is going to take in the geometry. It can be from after the capture attribute or before the capture attribute, it doesn't make a difference, but let's just take it from after the capture attribute, and you get a min and a max value. Now technically, if you take the average of the min and the max, you will get the center point of this particular point, which is going to be the location. So to find the average, we have to first add them by searching for vector math nodes and plugging the min into the first socket and the max into the second socket. Then to divide it by 2, we can search for a vector math node, and we could divide it by 2 on all of the axes, but instead of doing that, we're going to just change this to scale and scale it by 0.5. And if we plug this vector in here, we can finally plug this vector into the greater than node. But now the problem is this is currently a vector, but we just want to find the distance or the length of that particular vector. So to do that, we can again search for another vector math node, plug that in right here, and change this from add to length, and then plug this value into the first socket of the greater than node. So with this setup, we're going to get the position of this particular point, and we're going to check if that position is greater than the radius, and in that case we can actually plug this into the switch socket and use the other set position node. However, I don't want to check if it is just greater than the radius, because if this sphere is slightly larger, the sphere will actually exit the bounding box. So let's actually draw that. Let's say this is the bounding sphere, and we have our sphere present somewhere like this. In that case, since the center is still present within the bounding sphere, it's going to continue moving in this direction, and there's already a bit that's crossed the bounding sphere. So I really don't want that. I want it to be such that if we have it and the edge comes close to the bounding sphere itself, it should get pushed back, and that's why we're going to go ahead and subtract this bouncing sphere radius from this bounding sphere radius, and we're actually going to subtract more than the radius of the bouncing sphere. So we'll press Shift A and search for a subtract node, which is actually a math node set from add to subtract, and let's subtract the bouncing sphere, and this way it'll rebound back the moment it touches the sphere, but it's not necessary that it's going to calculate exactly when it's touching the sphere. Now we could do that with substeps and things like that, but I don't want to get that heavy for this simulation. So what I'm going to do is search for another math node, switch it to multiply, and make it a value of 2, such that when it comes 1 meter towards the edge, it's going to bounce back. So there will be a little bit of padding space as well. So now we have to figure out how it can bounce back, and to do that, this set position, we actually just have to use the position that we're getting here. So let's take this, plug this into the position, but we want to not keep it in the exact same position. We want it to get pushed back a little bit, and to push it back a little bit, all we have to do is search for a scale node, which is a vector math node, switched to scale, and then change this to maybe 0.9, and that way the position now gets pushed back to 0.9 times of what it was, and that actually gives it a velocity in the inward direction. Hopefully that makes sense. It's the same thing that we've done in previous tutorials of simulation nodes, so do check that out. Now make sure that you plug this geometry into the geometry, and this set position is going to go into the switch. But now if you actually look at it, it's going to get perfectly pushed back. It's going to go till the edge, and it's going to get perfectly pushed back, so it's going to move only in a straight line. We don't want it to move in a straight line, we want it to move in a random direction. So to get that random direction, after this set position, we'll press Shift D and search for another set position, and for this we'll press Shift A and search for a noise texture, which is going to give us our random vector from the color socket. But as usual, the noise texture is centered between 0 and 1, which means it's centered around 0.5, but we want it to be centered around 0 so that we get equal amounts of negative and positive directions. So I'll press Shift A and search for a vector math node, switch it from add to subtract, and subtract 0.5 and plug this color into the first socket, and then we want to actually be able to control the strength of this noise texture. So I'll search for another vector math node, switch it from add to scale, and maybe I'll scale it up by something like 2. And I'll plug this vector into the vector and plug this into the offset. So now if you think of what this setup did, you should be able to figure out how it works. So right now, if let's say the sphere has come too close to this edge, the first set position is going to find this particular position and then scale it down to maybe something like this, and then set the position of the sphere here. So now the position of the sphere is going to be over here. Then we're going to set the position again with an offset of something that this noise texture gives. So suppose this noise texture gives a value in this particular direction, it's going to shift to this particular direction, and so the new velocity is going to be from the old position where it was to this new position, and it's going to move in that direction like this. So it's going to continue moving in this particular direction now. Hopefully that made sense, but let's continue further. If you have any doubts, do comment it down below. I will do my best to clarify it. The next thing is this particular noise texture right now, it's always going to be the same if it hits the same position, but I want it to change over time. Let's suppose it does hit in this particular space again. It shouldn't move back in the same thing and get caught into a single loop again. And for that, I want this noise texture to be changing every single frame. So I'll change this to 4D, search for a scene time node, and simply plug the frame into the W value. And now it's going to be changing every single time. So with all of those changes, let's go back to frame 1 to reset the simulation and play the simulation. Now you should be able to see the sphere bouncing around in random directions, and it's always going to stay within those 5 meters. Now it's actually moving in 3D, so it's fairly hard to tell, but it is moving in random directions and it is staying within the sphere. So we can increase the end time to something really large so that it continues for even longer. But yeah, you can see how it's moving around in random directions and staying within the sphere. So that is pretty much all there is for the simulation portion of it. Now we actually have to create the bounding sphere that continuously changes according to this thing's position. So let's start dealing with that. So let's shift this group output all the way to the side and then add in an actual icosphere, which is going to be present as the bounding sphere. So let's press Shift A and search for an icosphere. And for the radius of the icosphere, we're going to use the radius that we've selected over here, and we can just drag that and plug that into the radius. And for the subdivisions, we can increase it to something like 3. And to see both the icosphere as well as these points, we'll have to use a join geometry node. So let's press Shift A and search for a join geometry and plug that in just before the group output, and then Alt right click and drag in between these two to connect it. Remember, for this Alt right click, you need Node Wrangler to be switched on, so keep Node Wrangler on. Now we want to find the position of the inner bouncing sphere, and according to the position, we want to delete a bunch of faces. So again, there was another caveat that I had to fix for doing that, so we'll work through that right now. So let's press Shift A and search for a compare node, because we want to compare the position or the distance of this particular bouncing sphere to the position of these points, and if it is too far away, we want the points to be deleted. Now there's two issues with that. Let's start off with the first issue, which is actually figuring out the position of this bouncing sphere. If we were to simply take the position by searching for a capture attribute node or even a sample index node, we wouldn't be able to get it. So let's actually search for a capture attribute first. We're going to capture the position, which is a vector. So let's change this from float to vector, and then press Shift A, search for a position node, or we can simply select this position node and press Shift D to duplicate it and then plug this into the value. Now this is giving us the position of this particular point that we created over here and moved around according to this simulation. Then to get the position of every single point in this particular sphere, we can simply use a position node. So let's take this position node, press Shift D and plug it in here. Now to find the distance between them, we can press Shift A and search for a distance node, which is a vector math node switched from add to distance. Now if you plug this position in here and take this attribute and plug it in here, this value should give me the distance between our original sphere and these points. So we can technically check if it is greater than a specific value, we want it to be deleted. So let's search for a delete geometry node, plug that in over here and plug this result into the selection. Now the issue that we're facing is that clearly something very random is going on, and it's not even updating with respect to the original position of this smaller sphere. So we need to figure out why that's happening and how we can fix it. So the actual issue is that, again, this sphere, the field can't really be updated every single frame for every single point. When we use this greater than node and we compare the distance, it's finding the distance between different points, and Blender just doesn't know how to work with that. So the solution that I went with is just doing the same thing that we did over here, which is finding the bounding box, the length, the average, and then the length of that. So let's plug this simulation output into this bounding box geometry, taking this value and plugging that into the compare node and using this for all of our comparisons. Now, to find the distance between the positions and the position of the sphere, remember in vectors, if we subtract them, we get a vector between them, and the length of that is the distance. So we don't actually require this length node. We can directly use the position over here and use this position here. Take those two, plug that in here, and now we get the distance. But the distance has its own issues, so we'll deal with that in a second. But let's just look at what happens if we use the distance for now. Now we get an animation that actually works. However, in this situation, this works perfectly all right, but you could face situations where this doesn't work as well. And that's because, let's say we have our sphere ending here. We have this smaller sphere present somewhere here. We have this particular distance. Now let's say the sphere moves towards here, and we want this region to start getting deleted because it's too far away from the sphere. Because we're using this distance between this sphere and the position of these points, you will reach situations where the position of these points is now further away from this particular point, because this now has to go this extra distance, and so these points will start getting deleted before this point gets deleted. I'm not sure how I can physically show you this, but okay, let's actually physically show you what's going to happen. That way you'll probably get a much better understanding. So let's, for now, just search for a separate set position node, then take this point, plug that into the geometry over here, and plug this output. Remember, I'm just doing this to show you what would happen, so you don't have to do this part of the tutorial right in there. And now if I also plug this into the joint geometry so that we can actually see the point. Okay, let's actually increase the radius of this point so that we can see it better. Let's give it the same radius as bouncing sphere radius, just for visualization purposes. And yeah, now let's move this sphere. You see, as we go back, it starts disappearing from the top again. So let's increase the subdivisions on the icosphere so that it's much smoother and you can see it even clearer. When we move away, we wouldn't expect these areas to be removed first, right? As we go further away, we'd expect this region that's technically furthest on the x-axis to be deleted before these get deleted, but that's not happening. So in this situation, as the sphere moves away, we'd want this region to start getting deleted first so that it looks like this, and then as the sphere moves even further away, we'd expect this region to get deleted and so on and so forth, so that there's literally like a ring remaining. But that's not going to happen in this situation because, as I explained, as we move away, this distance becomes further than this distance over here. So that's why that doesn't happen, but we need to fix it. So now let's delete this and figure out how we're going to fix that. And we also don't need this particular capture attribute anymore, so let's press X and delete it, plug this right in directly, and plug this into the joint geometry. Now you can in fact see it happening over here as well. When the distance is really high, or at least it's moving in the opposite direction, it disappears in that specific way where it becomes smaller from the outer edges. So I don't want that. Of course, if you prefer that, you can go ahead with it, but let's figure out how we can fix that. So the way I'm going to go about fixing it is by actually not using just this position and distance. Instead, we're going to find the difference on each of the axes separately and delete it accordingly. So let's press Shift A and search for a separate XYZ node, plug that in after the position, and now we have the X position, Y position, and the Z position. But we want this separate X, Y, and Z for the actual vector that goes from the sphere that we have bouncing around to the outer points. And to get that vector, we just have to subtract. So we search for a vector math node, change it from add to subtract, plug this vector in here, and then we can separate this out. So now the output of this is a vector that's going from this bouncing sphere to the points present in the bounding sphere. So hopefully that makes sense. So this output is every single one of these vectors. So this vector, this one, and so on. It's every single one of these vectors. Now we can separate out the X, Y, Z, and we can compare for each X, Y, and Z value. However, again, since we want just the length and not the displacement, we don't want it to be a vector value, which means we don't want it to be negative and things like that. So let's press Shift A and search for a math node and switch this from add to absolute, and that way we no longer will get any negative values. We will get only positive values, so we can plug that in, and now we can use this to compare it with whatever distance you want. So let's use another node to compare the distance because we want the same distance on all of the axes. So let's use a value node. Let's label this as max distance. Anything over this max distance will be deleted, and let's search for a compare node and plug this max distance in here and this value in here. So if it is greater than this distance, it should get deleted. So this value is what should go into the result. However, we're doing this only for the x-axis, but we need it to be on all of the axes. So let's just duplicate this absolute and greater than node by pressing Shift D twice, once for the y-axis, once for the z-axis. Now plug the y in here and plug the z in here. And then once you've done that, we need it for any of these. So if any one of these is on or greater than, the point should be deleted. So we'll search for a Boolean math node, switch the type from and to or, and then plug this this result in here, this result in here, then duplicate this OR node again, plug the output in here, this one goes in here, and now if any one of these three is true, it should get deleted, so we plug this in here. Now the max distance that we wanted was around 3 meters, but right now we see everything is deleted, so we have to find out why that's happening. And that's one issue that it could be, is we haven't connected this into the actual compare node. So let's plug those in, and as soon as we do that, we get all of our points back and they are moving along with the sphere, which is exactly how we wanted it to be. So that looks perfect in my opinion. Of course, if you want, you could use the other mechanism in case you don't like the way this forms these circles and things like that. I personally thought that's how it should be, but maybe the other method was better. So it's really up to you and what your stylistic preferences are, because right now even I feel like this is looking a bit too squarish. So of course it's good to learn how to do different things, but let's see, I might render it out using a simple distance between this and the position. Anyway, the next thing that we have to do is actually convert these to points and instance on the points some hexagons. So let's reduce this subdivisions back to 3 and then come here and search for an instance on points node and plug that in right here. Now for the instance, we'll press Shift A and search for a mesh circle and we'll plug that into the instance. But I'm going to reduce the vertices down to something like 6 so that they're hexagons, and then we have to play around with the rotation. Now remember, the rotation has to be oriented according to the normals, but essentially if we just find the direction of the position, since it's centered around the origin, the direction of the position or the position vector will be the same as the orientation that we want. So we can just search for a sample index node, plug this geometry in, and then change this from float to vector. And for the value, we're going to search for a position node, plug that in, and then we want it for every single index, so we search for an index node, plug that into the index. And now we can't directly plug this into the rotation because we have to align it to the Euler. So let's search for an align Euler to vector node, plug this into the vector, and we want to align it about the Z and plug this into the rotation. So now it's going to face the actual surface of the sphere. We can go ahead and reduce the radius quite a bit, and we can change the fill type from none to n-gon so that we actually have a face. Now if we play the animation, this is what it looks like, and that's all right because that gives that sci-fi look. Next, we want actual materials for all of these, so I'll press Shift A and search for a set material node, plug that in and give it the default material. Go to the materials, change the name to hexagons, and then press this plus button to create a new material slot, add in a new material. This time we're going to call this as sphere, and we're going to give that to the sphere down here. So press Shift D, plug that in over here. Remember, this node is coming all the way from the output, which is the point, but we actually still have it as a point and not a sphere. So first we'll just assign the material as sphere, and then we'll press Shift A and search for an instance on points node, and we'll instance onto it a sphere. So just search for an icosphere, change the radius down to the radius that we selected right at the beginning. Let's select this, plug this into the radius, and subdivisions, let's give it a subdivision, so something like 3 or 4, plug that into the instance, and then we have to set shade smooth. So search for a set shade smooth node, plug that in, and you are officially done with the geometry node section. Now we'll just do the materials, backgrounds, set everything up, and be done with it. So let's go to the output properties, change the frame rate to 30 frames per second, and frame will keep it at, let's say, 600 so that it's a 20-second long animation. Output folder can be wherever you want it to be. File format is going to be FFmpeg video. Encoding is going to have a container of MPEG-4 and an output quality of perceptually lossless. Then in our render properties, we're going to switch on bloom and screen space reflections, after which we'll change our geometry node editor to the shader editor, and we'll switch our viewport shading from solid to rendered so that we can actually see the changes that occur, after which we'll select our light, press Alt G to clear location, and then we'll start off with the actual materials. So let's select our geometry node object again, go to the materials, let's choose the sphere first because it's already selected. Let's go down and change the shadow mode to none because I don't want the shadow of this light to appear on these hexagons. Then I'm simply going to increase the emission color to a bright white, increase this emission strength to something like 3, and that is now our sphere. Next, for the hexagons, let's select it by coming up here, choosing hexagons, and then we'll make these very metallic. We'll keep the roughness at something fairly low, maybe 0.3, and we'll give them a slightly bluish base color, and that should seem all right. Next, for the light, I want to give the light also a slightly bluish color, so let's just select it and give it that bluish hue, and that's actually it for the materials. Next, I want to create a background, so I'll press Shift A, search for a mesh cube, scale the cube up by quite a bit, then press tab to go into edit mode, select face select over here, select the first face, press X to delete faces, then press tab to go back into object mode, leave it as is and just scale it up a little bit, and that seems all right. But I think I'm gonna require the walls to be further on the y-axis. So I'll press S, Y and scale it up. Then I'll press G, Y and move it to the front so that the back isn't too far off. Then I'll select my camera, press Alt G to clear location, Alt R to clear rotation, then press RX90 to rotate it on the x-axis by 90 degrees, G, Y and drag it back, and then press 0 to go into the camera view. Okay, so now the camera is oriented in the wrong direction. So I'll press RZ180 to point it in the right direction, and then press 0 to go into the camera view. Then we'll go to the camera properties over here, change the focal length down to something like 18, and that should be the effect. I don't want the shadows to be this sharp, however. So to fix that, I'll choose my light, increase the radius by quite a bit, and that should make the shadows much softer. But again, you might just not want shadows at all. So we'll reduce the radius back to 1, select our geometry node object again, go to hexagons, go all the way down to shadow mode and make it none. Then with our background cube selected, let's add in a new material for it. Just increase the metallicness all the way to 1 so that there are some nice reflections that go on, and let's reduce the roughness as well, go down to 0.3, and that should be all right. So with that, you get this particular animation, and when you're happy with everything, you can go ahead and press render animation. So I know that was a long one, but I really hope that you learned the different techniques that can be used and why we do it, so that you can apply it in your own animations to get stunning results. I highly recommend you check other videos in my simulation nodes playlist, because that will generally give you the basis that's required to create a huge number of animations, and simulation nodes is really powerful and is only going to get more powerful by the day. So if you really want to learn the next big thing in Blender, do try out simulation nodes. And thank you so much for watching till the end. The watch time really helps me, and until the next video comes out, keep creating and stay creative.